concept of zero is one of the most fundamental and important ideas in mathematics, yet its development and discovery is a fascinating and little-known story. The ancient Mayans and Indians were among the first civilizations to develop the concept of zero, and their contributions to mathematics continue to shape our understanding of the world today. The Mayans, who flourished in Central America between 2000 BCE and 900 CE, were skilled mathematicians and astronomers. They developed a sophisticated system of writing known as hieroglyphs, which included a symbol for the number zero. This symbol, a shell shape, was used to represent the concept of nothing or absent. The Mayans used zero in their calculations and in their calendar, which was one of the most advanced of its time. The Indians, on the other hand, developed their own concept of zero around the same time as the Mayans. The Indian mathematician and astronomer Brahmagupta was one of the first to formally describe the concept of zero in his book Brahmasya Siddhanta, which was written in 628 CE. He wrote about the properties of zero, such as how it could be used to represent the absence of value and how it could be used in mathematical operations like addition and subtraction. The symbol for zero used by the Indians was a dot. It's important to note that despite the similarities in their development, the Mayans and Indians' concepts of zero were not known to each other and the development was independent from one another. The concept of zero was not widely adopted in Europe until the 12th century, when it was introduced by the Persian mathematician Muhammad ibn Musa al-Khwa Resmai in his book, which was later translated into Latin as Algorithmi de Numo Andorum, which means algorithms of the Indians, and the word algorithm comes from the name of the author. From there, the concept of zero spread throughout Europe and the rest of the world, and it became an essential tool for mathematicians, scientists, and engineers. Today, the concept of zero is used in countless applications, from basic arithmetic to advanced scientific and engineering calculations. Without the contributions of the ancient Mayans and Indians, our understanding of the world would be vastly different, and we would be without one of the most important and powerful ideas in mathematics. In the early 17th century, a French lawyer named Pierre de Fermat scribbled a note in the margin of a book he was reading. The note, which has become known as Fermat's last theorem, stated that there are no whole number solutions to the equation x to the n plus y to the n equals c to the n when n is greater than 2. Fermat claimed to have a proof, but it was lost when he died. For over 350 years, mathematicians attempted to prove Fermat's last theorem. Many of the greatest minds in the field, including Leonhard Euler and Carl Friedrich Gauss, worked on the problem, but it remained unsolved. Finally, in 1995, a British mathematician named Andrew Wiles announced that he had a proof. Wiles had been working on the problem for over 7 years in secret, and his proof was so complex that it took the mathematical community over a year to verify it. Wiles's proof relied on a new area of mathematics called the Wiesel theory, which had been developed in the 20th century, and a special case of the problem that was first proven by Fermat's contemporary, the Dutch mathematician Tenniama. Fermat's last theorem is considered to be one of the most difficult mathematical problems ever solved, and Wiles's proof marked a major achievement in the field of mathematics. It also demonstrated the power of collaboration and the ability of modern mathematics to solve problems that were once thought to be unsolvable. Geometry, the study of shapes and sizes, is one of the oldest branches of mathematics. For centuries, the work of the ancient Greek mathematician Euclid was considered the gold standard in geometry. His book Elements laid out a set of axioms and postulates that were thought to be self-evident truths about the properties of space. However, in the 19th century, two mathematicians, Nikolai Lobachevsky and János Bolyai, independently discovered a different type of geometry known as non-Euclidean geometry that challenged the long-held beliefs about the nature of space with your own words. Nikolai Lobachevsky was born in Russia in 1792 and began his studies in mathematics at Kazan University. He was fascinated by Euclid's Elements and spent much of his early career trying to understand its underlying principles. In 1826, while working on a problem related to the parallel postulate, the fifth postulate of Euclid's geometry, he stumbled upon a startling discovery. He realized that it was possible to create a consistent system of geometry in which the parallel postulate did not hold true. In other words, in this new system, there could be multiple lines passing through a point that are parallel to a given line. He published his findings in the paper Geometria in 1829, but it received little attention. János Bolyai, born in Hungary in 1802, was also captivated by Euclid's geometry from a young age. He too was working on the parallel postulate, and in 1823 he also discovered a non-Euclidean geometry in which the parallel postulate did not hold. He published his work in 1832 in the appendix of his father's book Tentamen, but it was also overlooked. Both men were working independently and unaware of each other's work, but their discoveries were groundbreaking. They had shown that there were other consistent systems of geometry in addition to Euclidean geometry, and that the Euclidean geometry was just one of many possible geometries. Their work laid the foundation for the development of non-Euclidean geometries, which would have a profound impact on mathematics and science. The discovery of non-Euclidean geometries was not immediately accepted or understood by the mathematical community. Many mathematicians and scientists of the time believed that Euclidean geometry was the only true geometry and that non-Euclidean geometries were a mere mathematical curiosity. However, over time, the work of Lobachevsky and Bolyai began to gain more recognition and acceptance. In the decades that followed, non-Euclidean geometries were developed further by other mathematicians, including Bernhard Riemann and Felix Klein. They realized that the non-Euclidean geometries could be used to model the geometry of the universe, and they began to explore the implications of these new geometries for physics and cosmology. The discovery of non-Euclidean geometries had a profound impact on the field of mathematics and science. It showed that there were multiple consistent systems of geometry, and that Euclidean geometry was just one of many possible geometries. It also paved the way for the development of new branches of mathematics, such as topology and differential geometry. In conclusion, the discovery of non-Euclidean geometries by Nikolai Lobachevsky and János Bolyai in the 19th century was a revolutionary moment in the history of mathematics. Their independent discovery of non-Euclidean geometries opened the door for the development of new branches of mathematics. Their contributions to mathematics continue to shape our understanding of the world today. The development of abstract algebra by Évariste Galois in the 19th century was a significant achievement in the field of mathematics. Galois, a French mathematician, made contributions to the study of polynomial equations and group theory, which laid the foundation for modern algebra. Évariste Galois was born on October 25, 1811 in Berg-la-Reynie, France. He was a precocious student, excelling in mathematics and physics from an early age. However, despite his talents, he faced many setbacks in his academic pursuits. In 1828, at the age of 17, he failed his entrance exam for the prestigious École Normale Supérieure. This was a major disappointment for Galois, but he did not let it discourage him and continued to study mathematics on his own. Galois' early work focused on the study of polynomial equations, which are equations of the form of x to the n plus bx to the n minus 1, iteratively until plus cx plus d equals 0, where a, b, c, and d are constants and x is a variable. In the early 19th century, the study of polynomial equations was an active area of research, and many mathematicians were working to find a general method for solving these equations. Galois was particularly interested in equations that could be solved by radicals, which are expressions that involve only the four basic arithmetic operations: addition, subtraction, multiplication, and division, and the extraction of roots. In 1829, Galois submitted a paper to the Academy of Sciences in Paris, in which he presented his ideas on the solvability of polynomial equations by radicals. The paper was rejected, and the reasons for its rejection are not entirely clear. Some historians believe that the paper was too advanced for the reviewers to understand, while others believe that it was rejected because of Galois' young age and lack of recognition. Regardless of the reasons, the rejection of his paper was a major setback for Galois, but he did not let it discourage him and continued to work on his ideas. Galois' next breakthrough came in the form of a new mathematical concept, which he called a group. A group is a set of elements with a binary operation, such as addition or multiplication, that satisfies certain properties. Galois' work on groups was a significant departure from the traditional algebra of his time, which focused on solving equations. Instead, he was interested in studying the symmetries and structures of equations themselves. In 1832, Galois published a paper on his work on groups, in which he introduced the concept of a Galois group, also known as a Galois group of a polynomial. A Galois group is a group that describes the symmetries of a polynomial equation, and it was an important step in the development of Galois theory. Galois' work on groups and Galois groups was a significant departure from the traditional algebra of his time, and it was not well received by the mathematical community. However, Galois was not discouraged by the lack of recognition for his work, and he continued to develop his ideas. In 1832, Galois published a paper on the theory of equations, which contained many of his most important results. The paper was published by the Academy of Sciences, and it was the only paper that Galois ever published. The paper was not well received at the time, and it received little attention from the mathematical community. However, it contained some of the most important ideas that Galois had developed, such as the concept of a Galois group and the Galois theory, which is a method for determining the solvability of polynomial equations by radicals. Despite the lack of recognition for his work during his lifetime, Galois' ideas were later recognized as being ahead of their time. His work on groups and Galois groups laid the foundation for the study of abstract algebra, which is the branch of mathematics that deals with the study of mathematical structures, such as groups, rings, and fields. Galois' work on polynomial equations and the solvability of equations by radicals also laid the foundation for the study of Galois theory, which is a branch of algebra that deals with the study of the symmetries of equations. Galois' contributions to mathematics were not fully recognized until after his death, which occurred at the young age of 20 in a duel. He died on May 31, 1832, and his death was a great loss for the mathematical community. However, his work was later recognized as being of great importance, and it continues to be studied and applied in mathematics and other fields today. In conclusion, Maurice Galois was a brilliant mathematician who made significant contributions to the field of abstract algebra despite facing many setbacks in his academic pursuits. His work on polynomial equations and group theory laid the foundation for modern algebra, and his ideas continue to be studied and applied in mathematics and other fields today. Galois' work was not fully recognized until after his death, but his ideas continue to inspire and influence mathematicians and scientists around the world. His work was a great contribution to the mathematical world, and his legacy continues to be celebrated today.